Hello, everyone. I'm Kumar. I work on everything campus related, AP, switch, NAC, kind of touch, lucky to touch on all these different pieces. So specifically, what I'm going to focus on is what is it that we are doing from bringing together the wired and wireless network from a data plane perspective. You heard a lot about the monitoring control plane, a lot of the things that we are doing. And just to sort of take off on what Steve was showing so far, this concept of NetDL, where we are actually able to bring multiple data into a single data lake from which we can actually run modern software and then be able to create this root cause, is what allows us to extend the root cause, not just from the AP perspective, but also go into the switch, because they all log all their telemetry, streaming telemetry, everything into NetDL. So just a quick plug in there. So what are we solving here for the next few slides is fundamentally three things that we want to talk about. One is, secure AP deployments, and I'll expand on all these things. For local bridge mode, one of the big issues so far we have faced is, hey, I have thousands of APs. I need to define these VLANs in all the access switches, all the distribution switches. What is it that we can do something more intelligent than just go and manually defining all this VLAN? And finally, the third point is, roaming with an EVPN fabric, where your network is not just pure L2. It's actually now you're bringing some of the Ethernet VPN capabilities down to the access layer. There is a problem there because fundamentally it takes a long time to propagate the MAC address changes when a client moves from one AP to another AP. How far we can propagate those changes so that the convergence, the data traffic convergence happens. We're actually addressing that problem also here. In terms of this configuration, the theme is prevention is better than cure. We definitely believe in AIOps. We definitely want to use AIOps for a lot of our debug troubleshooting, but taking some steps and being more cautious at the configuration time and potentially flagging issues or potentially even disallowing some of these issues will obviate the need to go and troubleshoot at that point. And finally, as I said, mentioned, this is an integration from a wireless data plane perspective over and above what we are doing from monitoring and management plane. So a quick recap, this is where we left off last time. We basically talked about this controllerless architecture where we said, hey, on a given AP, on a per SSID basis, you can either do local bridging or you can do tunnel, and in tunnel we support VXN as well as EOGRE. The right side picture is kind of translating that into a real deployment. Just to call out here, we basically use this concept called MLAG or multi-chassis lag, where you can actually take two of Arista switch, make it look like a single logical switch. So if you're terminating tunnels from thousands of APs, we can actually terminate from 8,000 APs. So if you're terminating tunnels from those kind of scenarios, your blast radius can be very bad if the tunnel terminating device goes down. So this MLAG essentially provides that redundancy into the system. You will not lose anything, any data packet, no data traffic loss at that point if one of the switch fails. We also talked about how all these different tunnel technologies are sort of coming together from a data center and a campus integration perspective, whether it is IPsec coming from a branch, IPsec from some of our APs. By the way, I think one of you asked questions about the W318 and its ability to do NAT and so on. In over and above that, we actually support IPsec directly originating from the AP. So you can not only do NAT, you can actually choose to enable IPsec. So you can actually send encrypted traffic from the AP. So whether it's coming from that, MACsec, all these things essentially come together to the data center. And then we use this concept called VXLAN sec, which is basically the best of both worlds. We are combining the MACsec capability in hardware along with the ESPN AH that is part of the IPsec. So it kind of gives us the best of both worlds. So we don't have to put one protocol inside another protocol. Gives us a much more efficient way to transfer data between data centers. This is kind of where we left off last time.
So I'm thinking that wall plate access point, right? I'm assuming I can do the same exact thing with it. So we're thinking it's like a smaller branch location, or let's say
yes.
A remote user.
Yes.
That connects to my.
You can take W318. Let's say if 10 people, 20 people office, one single W318, set it to generate. You can actually operate in L2 mode or NATed mode. You can set it to send IPsec traffic, which will terminate on any standard firewall. You don't have to use Arista gear. Palo Alto, Cisco, Juniper, whosoever firewall you have, because it's just standard UDP 4500 traffic. And then once you terminate the IPsec, you send it into the corporate any which way you want.
Oh, so you're saying from that AP, I can terminate a tunnel to any, okay. Okay.
Exactly. Okay, so questions? Okay. The three features that I'm going to specifically talk about is AP.1x authentication. Don't laugh at it. We have some more to offer in terms of .1x authentication. It's a well-tested, known technology. How we are, doing the VLAN assignment in the case of local bridge scenario, and then roaming in the EVPN fabric. So, from an authentication perspective, the .1x authentication itself is nothing new, right? We've been doing it for the last 25 years now. Really, what are the things that motivates us to do is several of the financials are getting to a point where they want to make sure that an AP that's exposed, it's not inside a lock and key closet, is actually authenticated. The other thing is they also want to make sure an AP earmarked for a certain location is indeed that AP. It's not like somebody by mistake or the IT replace that AP with another AP. They just want to make sure that indeed the network is locked from that perspective. So to achieve both, what we are actually doing is basically there's a TPM in all our APs, so you can actually program the certificate. It comes with an Arista per AP unique certificate, but if you don't want to use that, you can actually use Agni, for instance, to generate certificate, or you can use third party. And we actually allow bulk certificate download through the CloudVision management software.
So if we do that, I assume the key store for the cert is on a TPM in the AP?
Correct.
Okay.
Absolutely.
And you can give us also a root cert if we want to just import that to our trust store and just be lazy.
Exactly.
Okay.
Exactly.
I vote for that second method. That's way easier.
Yeah, definitely a lot easier. So with this, basically what happens is we are actually doing one little thing. And by the way, it is not just locked only, even though I show Agni prominently here, it works with any other NAC solution, ClearPass or ICE or anything else that you may want to use. But one additional thing that we have done as part of this .1x authentication is the ability to send a VSA or a vendor-specific attribute as the AP is getting authenticated to further establish a trust relationship between the AP and switch. Why we are doing that? That's coming the next slide. So the reason we are doing that is when we do local bridging, where the AP is not tunneling traffic, it's just putting out properly formed Ethernet packet into the access switch. If AP is using 5, 6 different VLANs, you have to go define all those VLANs on every switch. So if you have tens of thousands of APs, thousands of switches, hundreds of distribution layer switch, all these have to be defined. By the very definition, this could be error prone, this could be a wieldy operation to handle. And if VLAN changes, you have to go back and redo all those things. Instead, what we are doing is we're using the standard MBRP protocol. I've just put a little bit more detail on where this MBRP is coming from. It's part of the 802.11 AK specification. What this MBRP does is it allows AP to send all the VLANs it's using to the switch dynamically, and it's also able to withdraw if those usage of that VLAN goes away. What this basically gives us two things. One is there is no more human error. Basically, AP is only sending only the VLANs it's using. Second thing is it's able to pull back if those usage of that VLAN goes away. So inherently, you're not leaving some VLAN defined exposed because the AP goes away, somebody plugs another device and starts using that VLAN. So it kind of inherently removes that. There are other implementations which tries to automate this by snooping the radius message that are coming in. So as long as it's radius, you can sort of get away with it, but the moment you go to RADSEC, you can't open that, it's encrypted. Finally, what it allows us to do is the ZTP or the zero-touch provisioning. It gives us one more way to effectively use zero-touch provisioning and be aware or be knowledgeable that it's actually done securely. It is not being done on a sometimes when the configuration is you have security holes that are coming up. The point I'm making is we're actually plugging the security hole also here. This VSA also allows us to do one thing, right? And again, I don't know how many people want to use this, but if you're authenticating an AP, let's say you have APs in the lobby and APs inside, you can basically choose to say only APs inside my corporate environment, I want them to be able to send the VLAN, but the APs in the lobby, I don't want them to send VLAN. So that's another additional thing. Even though both of them are getting .1x authenticated, you're able to select those set of APs which are allowed to propagate the VLANs it's using and count out the ones that you don't want them to use. This is a quick demo. I just thought, we'll show how this MBRP works. So on the right side is a console to a switch. Left side is a CVQ. Essentially, what it's showing is, hey, I'm going to the switch, enabling MBRP protocol, and then going to the AP, the CVQ, creating an SSID, assigning a VLAN, and it just starts showing up on the switch. That's really the main thing. In the interest of time, might fast forward this a little bit. So basically showing that there's no VLAN available yet. There is no registered VLAN. Now we're actually creating an SSID. And turning on the SSID. And that command line essentially runs a CLI every 2 seconds. That's really what it's doing.
So this is CVP then.
This is CVQ.
Okay.
Yeah.
So it can talk to the switches as well.
Yes.
Okay, because I haven't done that before. Okay. So.
And really, what we are seeing is the VLAN showing up on the switch, right? And this is not just only for the SSID static VLANs. Also, any of the dynamic VLANs that we are assigning will also show up as part of this.
So while we're watching this, it'll pre-provision the VLAN when you build the SSID. If you have somebody come on that gets a
dynamic
return
VLAN
for a different VLAN,
yes.
that is when that
is
populated.
Yes.
Gotcha.
So actually, what we are doing is we are actually using MBRP for both. So when I'm creating an SSID, yes, you can at that time use management to propagate that VLAN to both switch and the AP. But what we are saying is, once we have enabled this MBRP protocol on both switch and the AP, whether it is BSSID VLAN, the VLAN associated with SSID, or any dynamically obtained VLAN. So as a client authenticates when it gets a VLAN, all of them will show up over there, and it also gets withdrawn. So what happens is when we remove the SSID or turn off the SSID,
or the user goes away.
Yes.
Oh wait, exactly. If the user goes away, you remove the VLAN?
If it's user associated.
Yes, after a few timeout, it'll actually remove the VLAN, because fundamentally this is the whole notion of not leaving the VLAN exposed there forever.
But then what about the roaming? If the user, if I'm connected to a...
Oh, no. What does this is only specific to that switch, that interface.
But will it not still break the roaming? I mean, I'm missing something here. Because if you remove the VLAN, now if our user comes back,
no. So what I'm saying is,
it's going to take maybe.
No. When I'm removing the VLAN, I'm removing it only on that specific interface.
Right, but if I
go from another AP,
yeah,
that AP is connected to another physical interface on the same switch or a different switch.
Yeah, but then I move back to that AP. There's no VLAN anymore there.
No, the AP will still keep track of it, right? All it's saying is, look, right now I'm not using, so I can remove it. As soon as the client shows up, it can actually push the VLAN back.
Right, so what's the time period for that?
Usually, what we have seen is this happens, the MBRP advertisement happens in few milliseconds from when we get the VLAN,
That's
10,
what I'm
12.
curious. Will it break that roaming? Because I mean,
we have not seen it yet, but truth be told, we are still developing this feature. Okay. So I will definitely note your point, right? What happens if the client comes back? How long will it take? And do we need to, are we going to miss roaming? Or are we going to cause roaming by just removing the VLAN? That's, we'll test it and report it.
And you could likely even the sessions that clients have, right? Who's I don't know, if I'm running like for example, handheld device. Think of a handheld device running an SSH session to back to mainframe or telnet session, whatever, right? And pickers in warehouse picking stuff. I mean, they need to be that needs to be a pretty persistent connection. So if I'm roaming from one AP to another and I'm go back and all of that. And that whole VLAN needs to kind of get built out, even if it is.
See, I think that's what I'm saying. The build out over MBRP, what we have seen is from the time, that VLAN is activated in the kernel, in the AP, to the time it shows up on the switch is of the order of 10, 12 milliseconds.
That's
That's all it takes, because fundamentally it's a triggered event, right? What happens is the moment that VLAN is activated, MBRP is immediately scheduled, and it's one hop, right? It's definite.
But you could
Yeah.
you could likely pre-populate that just like
We
so look at the neighbor reports. Those are the viable roaming clients. Pre-populate those VLANs and say, all right, I'm on this AP. The neighboring APs all now have it.
So again, we'll do some tests and make sure that it doesn't break roaming. Obviously, right? We don't want to do that. That's the last thing that we want to create at this point.
Then on the switch side, from a configuration perspective on this, is it really just enable it on the port, enable it on the global level?
So what happens is that at least Arista implementation is you enable MBRP globally.
Yeah.
And then remember we talked about this VSA. So if you have enabled the switch configuration to honor the VSA coming from AAA, then it'll go and enable it on a port by port basis, depending on which AP actually presents that VSA as part of authentication. If you don't do that, then it'll get enabled. If you don't want to use that VSA, then it'll get enabled on all ports anyway.
Can I do it like so? Hey, I mean, if I create an SSID and it pushes out the VLAN, is there a setting where I can disable it? Hey, I don't want it removed once it gets pushed.
Yes, we will give that knob.
Okay.
Yes, definitely we'll give that knob.
Okay.
I mean, this is all config knob that we want to give the full flexibility. Yes, you can do that for dynamic VLAN. By the way, you can actually basically say don't withdraw even if the client goes away. Right.
Okay.
So you'll have the knob for all those things.
Chris made a good point. I think if you use the neighbor list and likely roaming candidates and pre-populate it to those, and then just withdraw it after the roam occurs from those that didn't need it.
Yeah.
That could be
that's
a way to speed.
That's a nice optimization. Yeah.
Is this available today, or is this an upcoming CVP release?
It's available in Switch. It's already, in fact, it's been available in Switch for the last 7-8 years. On the AP, this is in test right now. So we expect to get it out sometime towards the end of the year.
Thank you.
I have a question.
Yes.
The MVLAN is a standard, but doesn't work with RANSEC. So you've provided a security link.
No, what I meant to say was, see, if you look at some implementations, the way they are detecting that AP is going to use certain VLAN is they snoop the radius message.
Okay.
So when a client is authenticating off of AP, and AP is, it's the radius endpoint, sending a message, when the response comes from the AAA server, the switch actually opens the radius message and says, oh, okay, you're sending a dynamic VLAN. Let me instantiate it on my switch. So what I was calling out was when we go to RADSEC, we don't have that luxury anymore.
Right. Okay. But you haven't opened up a security vulnerability there.
No.
Okay.
No. In fact, we don't. We are actually closing what is possibly a vulnerability today, which is basically you don't have to snoop the radius messages at all.
Okay. Okay. Got it.
Yes, sir.
No, I didn't realize you were snooping that message back. So as
No. What I'm saying is we are not snooping.
You're not snooping.
We are not snooping. What I was referring to was some other implementation.
Copy. Okay.
Which are snooping the message, which has two issues. One is, what you pointed out.
Yeah.
Second thing is when RADSEC takes over, it becomes even difficult to snoop. That's the two things I was pointing out.
Gotcha.
Yeah, we don't snoop at all. Okay, finally, roaming plus EVPN. I think I kind of summarized most of the problem here. Forget everything. Just look at the steps 1 to 4 or whatever there. So the smartphone roams from, magenta to orange or whatever that is. Basically, our AP immediately right after it sees that MAC address, sends a link local packet saying, hey, I got this new MAC address. Switch 3 is now, in the past, when it was off L2, the switch 3 learned that MAC address and just flooded that MAC address to everybody. That was the L2 mode, learn and flood. Whereas when we go to EVPN, we can't do that anymore. We have to first give it to the CPU. CPU then schedules a BGP. BGP then needs to send the advertisement, needs to go to at least one of the distribution layer switch, and then it has to come down to all the other access switches. This can be, in the best case, about 100 milliseconds when the system is lightly loaded, but as the system load increases, it becomes very variable. It could be anything from 200, 500, 700, 800 milliseconds, even a second we have seen in some scenarios. That is a fundamental problem. Why? When we do EVPN, which is convenient because you're removing spanning tree and all the loops and all the issues associated with pure L2, that's the issue that we would run into when we go to EVPN. How we are solving this? Basically, I'll summarize it very quickly. Just focus on this red curve here, right? Really what it's doing is because we have a distributed control plane, every time a client roams, we know where this client came from, which AP it was part of and where it came from. All we are telling that AP is, hey, the client that you had, I have it now. Once I inform, then AP1 is opening a dynamic VXLAN tunnel. Stress the word dynamic, because if I have n APs, I don't have to have n times n-1 pre-nailed tunnels. These are what we call as dynamic tunnels. They get created when they're needed, and they get destroyed when the packet flow stops. So it's not a pre-nailed. In this scenario, what happens is AP1 opens a tunnel for a configurable period of time. The default is somewhere around 300 milliseconds is what we are thinking. We are still experimenting with some of this. And it's actually forwarding the packet, because fundamentally what is happening is the rest of the network thinks the MAC address is still with switch 1. So basically, switch 1 is then sending the MAC address, the packets to the MAC address to AP1, thinking that the client is still there. AP1 is just tunneling all those packets over to AP3 for a configurable period of time, before which, hopefully, the EVPN fabric converges, at which point we don't get that address anymore. We don't get packets for that address anymore.
Yeah. Are all APs aware of all clients connected to all other APs at all times?
They don't need to, right? Because what happens is, let's say I went through AP2 and then went through AP3, right? There is a small integration period. I didn't go into that specific detail. There's a small integration period, because if it's just transiting through that AP, I might still see it, but real owner is actually still AP1.
Right.
So there's a small integration period. If that client just went away, then I'm not going to keep track of that, right? Basically, the distributed control plane, in general, it has a knowledge of, which all APs has which MAC address.
Okay.
So I'm going to summarize real quick and hand it over to Robert. We talked about, securely deploying APs. This kind of came up with some discussion with some of our financial customers who don't want to see exposed APs. They want to make sure that it's indeed controlled and there's no rogue AP or some other AP sitting there. We also talked about how we can propagate the VLAN IDs securely from APs into switch roaming. My honest feeling is, as we are implementing, we'll fine tune and we'll come back with some more specific updates on what are the fine tuning we did. But we think fundamentally the algorithm works. Technically, it is de-risked at this point. And most important thing, this is an AP-only implementation. You can run it with any other switch. We don't care whether it is Arista switch. We'll be happy if it is Arista, but you don't have to necessarily have Arista switches. The key thing is no lock-in. In everything that I talked about, there's not a single proprietary implementation that we are putting in. And finally, we want to address the campus as a solution, not as individual point products.
My name is Robert Ferrullo. I'm a TME here at Arista Networks. I focus mainly on the campus side, but really more so on the Wi-Fi side. But what we're going to do here is, before we wrap up this session, we just wanted to take a look at a couple of design references. These are actual designs for some deployments that are in progress right now. The first one is for a very large higher ed campus design, and we'll point at some key characteristics here. Okay, so it's an end-to-end Arista solution. And the solution really is to basically replace a controller-based solution. And so what that means is that this customer was tunneling all of the traffic back to their core, or the spine here. And we needed to accommodate that, right? So that's one of the main reasons why we support VXLAN tunneling, is to accommodate traditional controller designs where they've tunneled traffic back. They're not bringing the VLANs out to the edge. So we accomplished that by creating tunnels from the APs all the way back to the spine of the core. And that doesn't require an additional appliance, right? There's no controller, there's no additional hardware appliance required. And we have great scalability. Kumar mentioned that's like 8,000 APs in one of these boxes. And the other thing I'd like to point out too is in the closets for the MDF, we have MLAG pairs. So we're not doing stacking there. We're doing MLAG pairs. So you get that high availability. You get that load balancing, and it's a standard-based solution as opposed to a proprietary stacking solution. And It's this network is designed basically to support 25,000 APs. So it's one of the largest campus in the United States and college campuses, and probably in the world. Really, I would say it's huge, and it's a big roaming domain too. So we've had to do bum traffic optimization both on the wired side and the Wi-Fi side. That means in terms of, reducing multicast traffic, northbound, southbound, multicast to broadcast, and then also, proxy ARP, et cetera, and then converting some traffic that is normally broadcast to unicast. And let's see, so that's that design. So that's one reference design. I'm going to move on. I'm going to go fast because I want to get to the last section on WIPs. So here. This is another reference design, and we're also doing some tunneling, but instead of tunneling all the traffic back, right, we're only tunneling the guest traffic back. The corporate traffic is actually getting broken out locally, so that's different than the previous design. And also, we are using EVPN here, layer 3 in the MDF, and so and we wouldn't be able to do that without some of the innovations that we have in terms of for being able to support fast roaming and so on. Again, we're still doing the bum traffic optimization, both on the wired and wireless side. One of the things to point out too is this 10RU750. It's a beast, 384 ports, and we can support 60 watts on every port concurrently. So that's something we're pretty proud of. And those are these devices here.